Sometimes you need to define a new element type in your analysis with the explicit solver, and the Abaqus element library doesn't have it. What's your plan for this issue? The answer is VUEL subroutine. Don't know how to use it? Watch this video.
Text documentations, simulation files, and so on. As mentioned, the first chapter talks about when we need this subroutine. This subroutine is for the user-defined element in Abaqus software. The VUEL subroutine is for the Abaqus explicit solver. And as mentioned in the software help, this is only for advanced users because the needed equations are very complicated and the user must have a complete understanding of finite element method, the element formulation, and applying it to the subroutine so that you can use the subroutine properly. You can use different UEL subroutines in your Fortran file and link it to Abaqus. The tips will be explained in the examples. How does this subroutine work? An article on our website shows a flowchart about the explicit subroutines, which is very similar to the standard ones. When the software starts solving a problem, after defining initial conditions, starting steps, step, and starting increment, we need some calculations to achieve some outputs. First strain stress and then loading. After calculating a strain and stress and defining loading and solving the problem by finite element, the results will be obtained. We have illustrated all subroutines that will be used in any part of this algorithm. VUEL that have two nodes with numbers 1 and 2. One side of this truss is completely fixed and U1 equal U2 equal UR3 equal to 0. On the right side of the truss, 2 degrees of freedom is prevented and it is only allowed to move in direction 1. Material properties of the truss are shown here. The radius of cross-section equals 5 centimeters, so the cross-section area equals 0.00785 square meter. We assumed that the truss is made of steel. The force applied is equal to 100 kilonewton. We will determine the amplitude of the force as a smooth type like this diagram. The free diagram of truss is illustrated in 3 dimensions according to the figure. Its coordinate in the local coordinate system is determined as x prime, y prime, and z prime. And coordinates in the global coordinate system is defined as u1, u2, and u3. We can obtain the length of the element by calculating Lx, Ly, and Lz, which are the amount of distance in 3 directions x, y, and z. The element length is obtained through the formula shown here. Stiffness and mass matrices are shown here. The stiffness matrix is equal to EA divided by LE, and LE is what is calculated here. In this case, we need a diagonal matrix of mass, so this matrix must be converted to diagonal. Since the value of the matrix is equal to 1, then in calculations you should only use the coefficient specified here. The transpose of displacement vector is shown here, and displacement components 0 are previously known, and L was estimated from there. In the next step, the internal force and energy in the previous increment are calculated by SVARs. And in the next step, the sum of internal energy changes and the previous step's internal energy equals the internal energy, which is subsequently stored with the force. In the next step, it is checked whether we have external force or not. Remember that, like the deload subroutine, we can apply loading in VUEL subroutine. To do this, in addition to coding in the subroutine, there are also some changes that must be made to the input file. In this case, the amount of external force applied is exactly equal to the amount of force applied to the model. A more complete explanation of all that has been said here is provided in the subroutine section. Note that in all analyses, the first check step and the second check step are performed. Then select the written subroutine file here. Finally, select the Submit option and wait for the analysis to complete. We see the problem-solving process by tapping the Monitor option. Like other analyses, the input file is first submitted, the time of which is specified here. Then we have the input file processor, which checks if the input file has a problem or not, which is important to use because we changed the input file. Next, we have the Abaqus packager, which runs at the beginning of increment 0. Finally, the explicit solver is called and solves the problem. As you can see, we have 3 elements here. The first element is related to user material and is displayed in a graphical environment. Elements 2 and 3, along with node 2, 3, and 4, are also clear here. There are different parameters such as displacement and reaction force in order to observe for each node. For example, to view the displacement values, select the props value option from the query tool and see the results for the selected node. We can also see the energy results. But because we didn't calculate the energy for VUMAT subroutine, the results may not be accurate. This example was to show how to use 2 VUEL and VUMAT subroutine in one problem, in a case that we defined user material or UMAT for different elements.
Hello everybody and welcome to our new video training package of Abaqus. VUEL subroutine in Abaqus. This package includes these sections. Introduction to VUEL subroutine in Abaqus. Workshop Part 1, Analysis of a one-element truss structure using VUEL subroutine. Workshop Part 2, Analysis of a one-element truss using user-coded external loads. Workshop Part 3, Analysis of multiple truss elements connected in series. Workshop 2, How to use VUEL and VUMAT subroutines in one model. Thank you for taking the time to watch this video. We hope it will be useful for you.